Now, if you remember in 8th standard, we have proved this property of equilateral triangle. That any point we take in equilateral triangle, PD plus PE plus PF is constant. Actually, it is equal to the height of triangle. Height of triangle. Okay. But then now I am going to write it. See, we have proved this by making 3 triangles like this and measuring the area. Because side length was A, we got PD plus PE plus PF is equal to A times what the height of the triangle, right? And therefore this was equal to H. But now what I am going to do is I will put the circle in center and drop perpendiculars and make it R. Okay, and then I will equate this area created by these 3 triangles, which are going to be congruent triangles. Again, the area of each triangle is going to be equal to, here it is A times this upon 2, that is area of triangle, which is equal to A times R, that is in radius, A times R in plus A times R plus A times R, that is 3AR upon 2. This is what is the total area of equilateral triangle if divided into 3 congruent triangles by joining the in center. So therefore what we get is PD plus PE plus PF is equal to 3R, which was our height. Anyway, it was in terms of height, and therefore this is what we get. Now, if we look at square, is this property square? If we put perpendiculars from any point P onto the sides of square, will they add up to PD? Let us now start saying PA1, this is A1, A2, A3, A4. Okay, PA1 plus PA2 plus PA3 plus PA4 is equal to, we would have converted into 4 triangles, and again by joining the in center with vertices you get 4 congruent triangles, is going to be equal to 4R. Is it true? Yes. Will it be true for pentagon, regular pentagon? Of course, yes, it will be true. So PA1 plus PA2 plus PA5 is equal to 5R. Now, we say that by using principle of mathematical induction, we can prove it for n-sided regular polygon. It will be P1, PA1 plus PA2 plus dot 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 plus PAN is equal to n times R. This is the first work that we would like to do, but this has nothing to do with our problem, because in our problem it is a regular polygon, but alternates are taken. Now, we are supposed to deal with only one-sided polygons, 2n. So the smallest polygon, which is regular and has even sides, is square. Of course, we should be able to say by watching it that yes, the theorem is true, because A1, A3 is 2R and A2, A4 for square, A1, A3 is equal to A2, A4 is equal to 2R. True. Now, when it comes to pentagon, what we are going to do is, no, we are not supposed to consider pentagon. We are supposed to consider hexagon now. So when it comes to hexagon, let me draw hexagon, which is regular. This is in center. Now here the trick that we will use is we will extend this. And those are going to be equilateral triangles because it is hexagon. Right? So I consider this as first permutation of equilateral triangle, and therefore suppose this is PA1, no, sorry, not from center but from anywhere, PA1, then I am not supposed to put on the second, I am supposed to put on the third, PA2, PA3 and PA5. I don't know. No, sorry. These are the odd ones which I have shown you. Okay. Now I will put it from PA2, PA3. Again, hexagon. Those are going to be opposite of each other. A3, A4, and this is PA5, PA6. Okay. So when I consider triangle P1 gives me original equilateral triangle result, that is PA2 plus PA4 plus PA6 is equal to 3R. Now, and when I change, I make, instead of these triangles, if I make these triangles, I will get congruent equilateral triangle. Yes or no? And when I look at this congruent equilateral triangle P2, which is equilateral, will give me PA1 plus PA3 plus PA5, which will be 3R. So for hexagon, it is true. Okay. Again, hexagon seems to be easy. Now let us have octagon. Octagon is going to be again easier, but still you are supposed to consider octagon. So this into this, into this, into this, into this, and suppose this is regular octagon. Then complete square like this. It is going to be square. So square 1 and another orientation of square 1 is going to be like this. Both of them are going to be congruent to each other. Therefore, their corresponding distances are going to be equal. So square S1 will give you PA1 plus PA3 plus PA5 plus PA7 is equal to 4R, and square S2, which is this, will give you PA2 plus PA4 plus PA6 plus PA9 is equal to 9. 8 is equal to 4. So are we done with octagon? Now let us do it. Let us do 10-sided polygon, which is going to give us 2 congruent pentagons. Okay. So let me draw pentagon first, which is relatively easier. Pentagon. And then convert it into 10-sided polygon. Okay, so what I have done is I have taken the 10-sided regular polygon, red one, and extended the alternate corners to get regular pentagon. I can call pentagon as P1, and another orientation of regular pentagon is going to be this. and this both of them will be congruent pentagons, and the distances are going to be same. And therefore, we are not actually proving it by induction, but we can say that this will continue because it worked for pentagon, it will work for septagon. So 14 is taken care. When it comes to 12, it will reduce to hexagon, and hexagon is already proved, therefore it will take care. And septagon, then 11-sided polygon you get after extending the corners. That means if you are talking about 22-sided polygon, then 11-sided polygon will give you this result in one orientation, and 11-sided polygon in another orientation. 26-sided polygon will reduce into 13-sided regular polygon in two orientations, and you will get this result, and so on. This result will continue for any 2n-sided regular polygon. That is what is the conjecture that we can make, and I think it is very convincing argument that we can say that we are almost done with the problem. बघा तुम्हाला पटतंय का?